Hey guys, I'm Wilson. This is WD Explains. This is my first video, so welcome to my channel. We're going to be doing weekly videos either in math, chemistry, biochem, physics, or maybe other topics too, if I get around to it. And today we're going to be looking at Q equals MC delta T, what it means, when to use it, and then some other pitfalls and stuff that other students might fall into. So, our challenge question for the day, or for the week, and the topic that we're going to be looking at is how much heat does it take to heat 100 grams of water from 20 degrees Celsius to 80 degrees Celsius? So maybe you already know, maybe you don't, but this is what we're going to be looking at today. So we have our formula here, Q equals MC delta T. So basically, what does this formula do? When can I use it? And what do the letters represent? So we can write out our formula, or write out our letters here. So our first letter we have is Q. Q here represents energy. And in this formula, it's going to be in joules, which is going to be J. We have our M. M represents mass of the material, which is going to be in grams, which we'll write as G. C is a bit of a unique variable. It's the specific heat capacity, and it's different for every material. And the unit for this is actually joule per gram degrees Celsius. So a bit of a unique unit there. And then at the end we have our delta T, which is our change in temperature. And this is going to be in degrees Celsius. So we'll just do a little unit analysis here to make sure everything works. So we have J equals G times joule per G degrees Celsius times degrees Celsius. So this is a little something I like to do all the time when I want to check and make sure I'm doing the question right and my units are right. So we can cancel out these, and what we're left with is J equals J. So we know that it works. So that's what is in this formula. So when can we use it? Well, we use it basically when we have a question where something is changing temperature or having some sort of heat added. And basically we want to analyze what the specific heat capacity is, or how much heat is being added, etc. So let's just jump back into our question. And yeah, well, let's revisit our challenge question here. So how much energy would it take to heat 100 grams of water from 20 degrees Celsius to 80 degrees Celsius? And now we have our C, our specific heat value here, of 4.18 joule per gram degrees Celsius. So let's start out by writing our equation. Q equals MC delta T. Then we can plug in our numbers we have here. We have Q equals 100 grams times 4.18 joule per gram degrees Celsius times 60 degrees Celsius. Plug that all into your calculator and you're going to get 25,080 joules. So, not sure how much you guys know about energy, but 25,000 joules is a lot of energy. This can also be written as 25 kilojoules, roughly. That's a lot of energy for just boiling half a cup of water. As we know, 100 grams of water would be 100 milliliters, which is just under half a cup. So that's a lot of energy. So an important thing to do when talking about Q equals MC delta T here is analyzing how different materials behave, like with their different specific heat capacities. So let's try this question with a common material, aluminum. How much energy would it take to heat 100 grams, the same mass, of aluminum from 20 degrees to 80 degrees Celsius? And we have our C here, which as you can notice is quite a bit lower than that of water. So we're dealing with 0.897 here. So this is the same amount of material going up the same temperature, but a different material. So let's see what happens. So we'll write out our equation here, and then we'll write out what we've got. So 100 grams times 0.897 joule per gram degrees Celsius times 60 degrees Celsius, which is our delta T again, if I didn't mention before. And our Q here is going to be 5,382 joules. So, as we can tell, as we know, that is quite a bit smaller than 25,080 joules. And that's pretty reflective of the trend of water having a very high specific heat capacity, which is a lot higher than any metal and actually most substances. And the reason for this, just a quick little chemistry lesson here, is that water, hydrogen bonds, as you might know, just draw a couple. So these are the hydrogen bonds here. And when you heat up water, you have to disturb these hydrogen bonds. As we know, it takes energy to break bonds. So it takes energy to break these hydrogen bonds that aren't present in other structures. Like when we have aluminum, there's nothing there. So we don't have to break anything. So it's easier to heat up aluminum and get these particles moving. But it's harder to get water particles to start moving and vibrating because of the hydrogen bonds. So what if we use the same amount of energy for a 200 gram sample of aluminum? So here we're going to use our same initial temperature of 20 degrees. We're going to use our C of 0.897 joule per gram degree Celsius. And then we're going to use M of 200 grams. And we're going to actually use Q of 5,382 joules. So let's set up our equation. And here it's going to be a little bit different. So we're going to have 5,382 joules equals 200 grams times 0.897 joule per gram degree Celsius times delta T. Now you notice here we are solving for temperature final, but you might have noticed that I didn't put 20 degrees in this. It's because it's a lot easier to just solve for the temperature change and then later find the final temperature from that than to try and insert it all in. So we'll just do a little bit of rearranging here. We'll bring these over to the bottom. And then we're going to have 5,382 joules divided by 200 grams times 0.897 joule per gram degree Celsius equals delta T. So if we calculate that out, we're going to get 30 degrees Celsius. Now, if you remember from the previous one, when we had 100 grams of aluminum, we had a delta T of 60 when it was 5,382 joules. When we had the same amount of energy with 200 grams of aluminum, it's a little messy, our delta T, I'll put that in degrees Celsius, was 30 degrees Celsius. So let you guys take a couple seconds to see if you can recognize the pattern here. Okay, so what happened here was that as we increased the mass by 2, the delta T halved. So it's pretty straightforward. Like if you double the amount of mass, then the temperature change will be halved because you use the same amount of energy, so you can only heat up the material half as much as you did before. So because there's no sort of exponents or square roots or anything in this formula, everything stays linear and good. So like if we had a 400 gram sample of aluminum, I'll let you guys guess what the delta T might be. Take a couple seconds. So if we had 400 grams of aluminum, the delta T would be 15 because it would be 1/4 of the 100 grams if we use the same amount of energy. So that's how you use the formula. So let's see when we shouldn't use this formula. So if I were to ask you to solve the question, if we have some water starting at 16 degrees Celsius, so TF would be -4 degrees Celsius. C is 4.18 joule per gram degree Celsius. And I asked you guys how much energy it took to cool the water down from 16 degrees Celsius to -4 degrees Celsius. And we all know that at 0 degrees Celsius, water freezes, equals FP for freezing point. If you guys were to tell me that you would use Q equals MC delta T and you would just plug it all in, your answer would be wrong for the energy. So there's another formula that we use called Q equals ML. So we have some familiar faces here. Q is still energy. I'll just put energy. And M is still our mass in grams. But L is a new variable here. So this is the latent heat of blank. Now it's not actually blank. This can be freezing, evaporation, etc. So this is basically the phase change that's going on. So actually what happens, like, so if a sample of water is going through freezing, it actually takes another quantity of energy to cross the barrier from being a liquid to a solid, or the other way around too. So this is going to be unique to each material and also to which state change. So the Q equals ml. The L will be different for freezing. So this might be L1, this might be L2 for evaporation, and so on and so forth. So this is always given to you in a problem if it crosses a freezing point, melting point, boiling point, any sort of that stuff. But that's a very, very, very common mistake, is just forgetting that at the phase change boundary, you have to use this Q equals ml. It's a very simple formula to use, but if you don't, you're going to be in trouble. Another problem, and why I mentioned the unit analysis before of J equals G times joule over gram degrees Celsius times degrees Celsius, is that it's pretty easy to use the wrong units too. Because say you're given kilojoules, well, kilojoules, remember we equaled out everything to joules earlier. Kilojoules does not equal joules. But also if something's given in kilograms, joule equals gram, well, kilogram times joule per gram degrees Celsius times degrees Celsius. These cancel out. These don't cancel out. So you have to make sure your units are correct. So you have to convert kilograms to grams, and you have to convert kilojoules to joules to make sure everything's okay. So these are the most common issues that students often run into in exams or homework or anything like that. So I'm going to let you guys try a video here. So I'll read the question. How much would 28 grams of wood be heated if the sample has a C value of 2.3 joules per gram degree Celsius and had 239 joules added, starting at 16 degrees Celsius? So I'll write out our variables here. Q equals 239 joules. Ti equals 16 degrees Celsius. M equals 28 grams. And C equals 2.3 joule per gram degree Celsius. I'll let you guys pause the video, and I'll wait for a couple seconds before we start up again, so give you a chance to pause. All right, let's get started here. So we'll write our formula out. Q equals mc delta T. We'll plug in our information here. So we have 239 joule equals 28 grams times 2.3 joule per gram degree Celsius times delta T. You'll notice again there's no 16 degrees Celsius in here because I saved that for later to make it easier. So we'll rearrange this. 239 joules over 28 grams times 2.3 joule per gram degree Celsius equals delta T. Solve this out. This gives us 3.7 degrees Celsius. So our TF equals Ti plus delta T. TF equals 16 degrees Celsius plus 3.7 degrees Celsius. And this gives us 19.7 degrees Celsius. And that's how we would solve that question right there. So that's it for this part of the video. Thanks for watching. I'm going to put a code in the video description and upload a Google Drive. And the Google Drive contains a free worksheet and another document, which will be the worksheet with the answers added in. I hope you guys learned something from this video. I hope you guys subscribe and like, and comment down below if you have any suggestions for what the next video should be. And thanks.